Yeah, so malloc, really slow, don't do malloc in embedded programming. Just like make an array bigger than, like as big or bigger than what you'll ever need. And just declare it global. And that will do everything that you wanted from malloc, right? Variables, like instead of variable size memory, instead of making an array that's n big, you make it max n big. Yeah, because like even if you declared a bit of extra memory, no one does. And yeah, if you make it global, then better chance of. This may be a bit of a relic of back in the day, back when I was your age. But yes, again, competitive programming style is to make these big arrays global. Yeah. Any further comments on that? Miles, if you have anything to add, you can. Yeah. This is again really bad in other contexts, right? Why are global arrays bad? Why are you taught in like 1511 don't use global variables?
Why would if you want to declare another similar one?
Yep.
Like, your neighbor is going to go out.
Yes, absolutely. So if you want to make something, it may have a naming conflict with some other variable. Yeah. Especially in what kind of context? Sorry. Yeah, workforce, but like, why is that going to be true in work? A lot of people doing different things. Let's like drill it a little bit more specifically. It's like different files, right? Yeah. So if you have one file and someone else has some other file, and you have global variables that each other don't know about, then that can kind of right? But in embedded programming, you never have this, right? It's one file. Only the three of you will ever look at it. It doesn't need to be maintained ever after this. And you know for sure that it will only run on this kind of system that have like well-known bounds on how much memory they have for you and stuff like that.
Yes.
So yeah, all the reasons why it's bad in every other context just don't apply here, and the very small upsides are working too. All right. So yes, declare your array, declare this array global, and it will be fine. I think if you get a little bit bigger than this, you start running into problems again. I think at like 100,000, so 100 million, you may again start having some trouble finding big enough arrays. I think 100 million is probably fine, but yeah, can be a bit dicey as you get closer and closer to memory.
I'm assuming that if you have to keep track of multiple variables other than just two, maybe like a hunger variable, we would make like a 3D array. And if
yeah, so you're going to make a 2D array for this one. Yeah. So it'll be a 2D array where the first dimension is 100,000, or make it like this, 100,000 and a little bit, and the second dimension will be like 500.
And I'm also assuming that we will store the cactus and all the board in a different array and
yes,
check it.
That's correct. But that array is much smaller.
Yeah.
So that's not much. Yeah, you're going to store the cactus.
Would this be bottom up?
Yeah. So this is considered bottom up DP. It's so you're going to run a loop over all the positions and all the distances to calculate this. Yeah. So what I've done here is called forward propagation DP. It's working out for this state, how does it contribute to future states? You could write this in a more traditional DP implementation by working out for this state, how is it calculated from states that have come before. There's like slightly more balance checking if you do it that way. So I've chosen this way for convenience, but it's all equivalent. Yeah, you're simply changing the scheduling of all the same arithmetic operations. Cool. The next problem to talk about, I'm pretty sure will be problem A. We can go back to the tutorial. We have, yeah, so important observation is that K is again up to square root of n, otherwise this would be no good, like not even worth thinking about what the recurrence is. If there are too many states, then yeah, if there are 10 to the 10 many states, you cannot possibly solve them all in 10 to the 9 amount of time, right? So you have to do something else. Yeah, and then exactly as we've talked about, This is the backwards. This is the like traditional implementation where you work out how is this state solved by the ones that have come before. And yeah, there is some bounds checking, which is annoying. Cool. So we get n times the square root of n, that being the size of the table, and each of those subproblems was treated in constant time, so it contributes only a constant factor to the complexity. Cool. L is next. Okay. Cool. I do not remember problem L. Cool. So we have a graph. If someone else is more familiar with the problem, feel free to jump in. Anyone? Go. Yeah. Go for it.
And don't you solve the question?
No.
What we went wrong. So you, yeah, so you share by one.
Also.
Yeah. And then you can. Yeah.
That's why leading companies are asking like
Like, he's talking about the other. He's talking about L. It's like in the range. Just like
That should work when it's
yeah. It's not like it's ready. It's like
it does. I'm pretty sure it does.
I need a workshop. No, I haven't gone into Instagram for 2 days. I don't want to do workshops. I swear, Instagram is not even here. Look. Dude, Instagram is 3 minutes. I can set the difficulty. I set it as like 1 minute per 1 push up per minute.
That's not bad.
I do not want to. I'm too lazy. Stay on.
Can you not disable it?
I should like not make it. Just so lazy. Mentally, I want to know this one.
Long as his,
Mentally lazy. Sorry?
yeah, I think I'm.
Like, I'm mentally lazy. That's not true. I'll find a way to go and give no matter what.
Start asking.
It's because you need to. You get it?
What do you mean?
Baby. Are you sleeping, you know? You shave, KJ? No.
Yeah.
Okay,
You can just see it.
There's no one behind us, show us.
Awesome. So in L, it's apparently somewhat standard, but also different graph problem.
If you share from my laptop.
Already in Teams or?
So if you share window laptop.
Okay. I see. Sorry. So yeah, so problem L is sort of going through a graph. You're going from node or junction in this problem 1 to junction n, and it's about trying to get to n as fast as possible within a given time. But instead of just like common, like it's not a typical weighted graph. The problem has like the extra fact that along each road or edge or whatever they're called in this problem, there is a speed before that global time t, and then a speed afterwards. So in this instance, all these roads have a speed prior of 1, and then after 1 second, they have a speed of 2 units per second. Yeah, and the goal is just once again going through. So because the time change happens simultaneously, we can just sort of do a greedy traversal through the graph. Where at every point, we're trying to see which junction is the one that we can reach next soonest. So I will figure out how to start. Okay.
It's just
So the way I had this was that with every given sort of edge, you basically have a few things you want to know about it. You want to know, obviously, which two paths it's going, which two junctions or nodes it's going between. You want to know the length of it, and you want to know the speeds on it. I'm first going to write a quick function that would calculate how long it takes, or what time it is when you end having traveled through that road. So let's just call the f travel. And what we need to know is we want to know the start time. So I'll call it t start. And we want to know some information about the road that we're going on. Let's call it road. Let's just call it directly the stuff that it's using. So we're L, we have U, we have, is it U and V? V and W. V and W. And then so what we need to know is that there are a few things. Either our time start, so t start, can be already greater than the global variable t, which is when roads are changing. And so obviously you would just be able to return, so that like the time when ends is just t start plus L divided by W, because you're already using the new updated speed. Alternatively, if you start before and you can still finish using that road before that time change happens, so you can just check that being TS plus L divided by V. If that is less than T, then it is just basically that thing I have up here, TS plus L over V. And then the in-between one is probably where sort of like a little trick comes in, but it's not that difficult once again. You can just sort of realize that in the time between T start until T, you've traveled a certain amount of distance. So you've already traveled U times T minus T start. And then you have, and so the amount of time traveled left, sorry, the amount of distance left is L minus that amount. And then so that is how much time you have left to travel after T. And so you return plus B. And then all of that is divided by W. All right. So does everyone follow why this function works? So that's just something that's useful, and we can sort of go back to this whenever we're trying to figure out how we traverse through the or the graph, sorry. So we start from 0, or node 1, or it's 1 index. So we go from 1. When we first read it through, I sort of made an adjacency list. So I know that 1 might map, for instance, if I can use the example, node 1 maps to node 2, and it also maps to node 3. And so I'm going to use a heap queue to keep that sort of, to keep a general idea of the next fastest node to reach. So I'm going to have everything first initially from my node 1 in a heap queue. So inside my heap queue, I'm going to have two things that I want to know. The parameter I care more about is the time that would take me to reach a certain node, but I also have to track which node I'm actually reaching in that time. So let's just call it the E, which is time to reach that node, and then let's call it node. And so for all the things starting from 1, I add that, and then I effectively just keep on iterating through this. And so every time I choose the next thing of lowest, so I keep pop to get the node that I can reach next fastest in a greedy method. And all I have to do is just check that I haven't already reached that node. So I'm going to just keep track of, let's call it.
Just one clarification.
Yeah.
So you mostly use Python, right?
Yes.
So for those who don't know, like heap queue is the equivalent like of priority queue or like say on C++.
Okay. Thank you for that clarification.
Does it have a library in C++?
Yeah. So it's in the queue library. It's called
Okay. Yeah, in Python, it's just import heap queue. So I'm just going to call this one PB. So it's just the fastest time I can get to everywhere. And we'll just initialize it as like, let's just say -1. And that's just done n times, where n is how many nodes I have. And so all I have to do is just every time I pop out the lowest, the lowest, and obviously the corresponding node. And then all I have to check is that my PB is still -1. And the reason for that is that my PB is a value, then that value is going to be higher than whatever this is. Because I'm doing it in a greedy way, I'm always giving the lowest time possible. So all I have to do is just check that if my PB low node is equal to -1, then I would continue with this. And so what I do is a very similar idea to what I have up here, where I sort of just once again add it, where I now do and once again, it's the time to end there. So we have now the lowest time. And so all we do is we just basically use this function where we now call f, and we have our previous t, let's call it t. We add in the values along all the things connected to low nodes, and we just add them once again. Should fun stuff better. Okay, so here, there is a for loop is that for all add to low node. We sort of keep it and we add in, or we add to our priority queue then, all of those based on the various rows linked to our low node. So L, U, or L, B, W. And then once again, we're running this for first parameter, which is the time it takes to end at that node. And we're also trying to get that new end node. Let's just call it. And so if we repeat this idea eventually, we sort of just iterate using the greedy idea, in which we're always trying to find the fastest way we can get to any node. And because of how things are set up, that is something that is allowable. It never makes sense to get to a node in a slower amount of time. That would never be optimal. And so as we go through this, as soon as we find a low node, so we just keep on repeating this. And then when low node is n, then you just return that function there. And the first time you come across n, because of how you sort of done the priority queue, it will give you the lowest time to reach n. That was a bit messy, and I might have been like using Python biased terms. Are there any questions? Oh, awesome. Okay.
Thank you, Greg.
You're welcome.
Okay, next problem.
Would you be able to do this in C without writing your own?
Yeah. Can you do it? Can you do this in C? Yes.
Without writing your own function. Because
So-
I was planning to write my own function, then I
Yeah,
was like,
so
no.
this is what Dash's algorithm. You want a priority queue. It's not as painful as some other data structures to write this off. It is possible to write your own priority queue in C. You basically use an array to simulate it, but because it's a binary tree, you basically can store the root in position 0, the children of the root in positions 1 and 2, the grandchildren of the root in 3, yeah.
You just have to make your own thing.
You make your own
like-
thing, and it works because a heap is guaranteed to be balanced enough that it doesn't have a bunch of empty stuff in it. And yeah, it's not as painful as writing, for example, a red black tree in C. That's awful. Yeah, so you can do it, and you can do it in arrays rather than dynamic memory. So it's not too bad. But yes, C++ gives it to you for free, so. And heaps are like reasonably fast. The constant factor on heaps is not too bad. Okay, let's continue on. Our next problem we're going to talk about is problem A. Alright, so in problem A, we have let's go. Problem A, we have a range. Is 1 to 10. Secret is M, some M within that range. And so we want to know for the worst case of what that secret number is, what is the least costly strategy that we can employ? And we want to report the cost of the strategy, right? So we want to.
We're given this penalty number.
Yes, you're also given the number B, which is the penalty to guess again. Yeah. So you want to guess down to this secret value M, and whatever you want to guess as cheaply as possible by some sequence of guesses, and report what is the most that minimum can. The rules of the guessing game were that if you guess lower than M, then you have to pay a bribe B in order to continue guessing. If you guess equal to or higher than M, then you pay however much you bid, but then the game ends. Cool. So
No, the game doesn't end.
You have to guess the exact amount.
you have to guess
like the guess amount.
Oh, you have to.
Yeah.
Did you get
That's strictly over. You have to pay the amount you just guess, and the game keeps going. And when you guess the exact amount, you pay that, game ends.
Ah, okay. Sorry, my bad. Okay, so you have to keep going until you know the amount itself. Cool. Thank you. Sorry, I should have read this more closely. Anyway, so yeah, I hope it's clear that the strategy depends very much on the bribe, right? N is 400 or up to 400, and the bribe can be really big, up to 10,000. Yeah. If N was say 100 and the bribe was maximum 100 is 10,000, then it's actually better to guess every single amount 100, 99, 98, 97, all the way down to 1. It's better to do this than to be under even once. Yeah. So yes, we would prefer to overestimate until we know the actual number than to get it wrong even once from the low side. So yeah, some very strange looking strategies may be better just because the bribe is so much, right? Whereas if the bribe is low, then you want to do something entirely different. Yeah. Cool. So any kind of approach where you try to guess the best guessing strategy in general seems kind of doomed. Yeah. So we can rely on the fact that we have a computer. Yeah, we can check a lot of stuff. Once again, I'm going to ask, how many different situations can you find yourself in during this game? What constitutes a situation? Like partway through the game, what kind of information could you know about what kind of information could you know about the secret?
We can say that the secret number is in range between L to R.
Yeah, it will be within some range, right? Whatever guesses we have made that are too low, it'll be greater than the smallest of, greater than the largest of these. And whatever guesses we made that are too big, it'll be less than the smallest of these. So the game state is a 10, low, high. Cool. All right. So that again, this is going to be a pair of values. These values are each up to n. So we have only about n squared many states, and n is only 400, which means that we have about 160,000 states. And if you think about it carefully, you'll see that you could actually afford to spend even about n time to solve each one of these states. So if I knew that the secret number was within this range low to high, what are my options? What can I do? And
we can try guessing every single number.
Yep. So we should consider what happens if we guessed each of the numbers and see what the outcomes are. So The best that I can achieve for the pair low, high. This will be the minimum overall possibilities.
Yes.
Yeah. Of let's call it mid. Between low and high, I'll put inclusive. Just to cover all my bases, tell me if I'm doing something unnecessary, but I think this is fine. And now if you guess some particular value mid, then what options are there?
If it's too high, it's going to be like low to mid -1.
Yes, so it could be that this guess of mid is too high, in which case we pay mid amount of money. And we add to that how much cost will the rest of the game will cost us, which is best of the remaining range. Now that we know that mid is too much, then we can guess low to mid -1. But there is another possibility. The amount we guess might be too low.
So you gotta pay the B and then B mid +1.
Fantastic.
This is the same as G.
Not exactly. There are some subtleties. It is certainly the same algorithm dynamic program, right? Because again, there are many pathways by which I could have got to that same interval. Yeah, there are many like sequences of guesses that could have led me to a state where I know that the answer is in the interval low high, but all of them can be solved in the same way. So you just take whichever was the best way of getting it. Yep. And I think this is the recurrence. That's it. Yeah. Cool. Now, there is one other subroutine that we have to talk about, which is in the previous one in G, we just said loop over all the positions, loop over all the jump distances, and do the thing. Yeah. Does that work here? If we go for low from 1 up to n, for high from 1 up to n, off we go. Can we run this recurrence like this? No, we cannot, because the order is important. In order to calculate this left-hand side number, we need the numbers on the right-hand side to have already been solved. Yeah. And if you just run outer loop where low goes from 1 up to n, inner loop where high goes from 1 up to n, then say when you get to best 1n, that will depend on things of the form best 1 mid -1, which we have done before, but it will also depend on best mid +1 up to n, and you have not done it. Yeah. The first parameter of the recurrence being anything other than 1 is still yet to happen. So we've not calculated any of those, and so we won't be able to use it. So you have to schedule these calculations of the best values in a good order. The order that you can rely on here is that big ranges always depend on smaller ranges. Yeah? Low to mid -1 and mid +1 to high are both strictly smaller than low to high. So you want to do all the shortest ranges first, then all the slightly longer ranges, then all the slightly longer ranges, and so on and so on. And best 1n is the very last one.
Yeah. So is it like building the segment tree where you start with the very small individual area
Similar.
and then you go back and
Segment trees,
no, like the same idea of making it.
it's, I mean, like some similar principles, but this is more of an analogy than a similarity for mine. What I would compare this to is if you have done algorithms, then the matrix chain multiplication example that we did there. Anything that involves taking a big long string, a big long sequence, like subarray, and splitting it at some point that's like calculating the recurrence, and then working out each side of the split, what's the best that you can do. So the classical example of this style of problem is you have a sequence of matrices that you want to multiply all together of varying dimensions, and you want to place the brackets for the multiplication in such a way that you calculate the matrix multiplication, like the big matrix multiplication, in as few operations as possible. But yeah, same is true here. We want to work from like basically your outermost, like you need two loops to go over all of these, but the outer loop should be in order of high minus low, the width of your range. Yeah. So your outer loop goes from where high minus low goes from 0 up to n. 0 up to n minus 1, and then your inner loop can actually be anything but low from 1 up to low from 1 up to n. Okay, and so the time complexity here will be that n squared states each take n amount of time to solve because you need to run a loop between them. So it is big O of n cubed, when n is 400. If you do the arithmetic, this comes out to about 6.4 times 10 to the 8.
Oh, yeah.
Yep, 4 cubed.
Yeah.
Yep. Which might seem very touch and go, right? Might seem very close to exceeding time limit. However,
I think it's 64 times E6, right? Which is E6.
Oh, you're right.
Yeah.
Sorry.
E8.
Thank you. I'm stupid. Sorry.
Nah, everyone's like it's a fight it is.
I was gonna say, even if it was E8, there's significant savings because high is always greater than low or greater than or equal to low, and there are many more short arrays, like short sequences, than there are long sequences. So mid actually doesn't take n many steps most of the time. It takes like less than half n steps on average. So there's like a couple more constant factors to be saved in this very back of the end. But yes, as it turns out, there's a factor of 10, right? Cool. Anything else to be mentioned here? What's the actual answer? It's all well and good working all these out. What's the answer?
Is it best one low as in 1 and high as in n?
So best 1n is the amount that you will pay at the very end. Oh yeah, that's true. Yes. Yeah. So best 1n is the best that you can achieve from the silent state. So that is the answer. Very good. And one other thing is base cases, right? It's all well and good having this recurrence, but there's going to be some states where there is nothing to iterate over. There's very little to iterate over. What are the smaller states where we can't solve them by recursing onto other stuff? And what are the solutions to this?
There are two cases here in which if low is like higher than high.
Yeah, so
it's
if
0.
low is bigger than high, then this is nonsense and it shouldn't happen. We should just never depend on such a state. So you can actually garbage initialize this and it should be fine. But ideally, yeah, just make it 0. Actually, you can make it plus infinity so that it never wins at best. It never wins at min. That's the way to do it.
And the other one is like where the length of the range is 1.
Exactly. The real base case, the one that we actually depend on, is when low equals high. So then you know the amount, and then I guess I'll have to reread the thing, but yeah, like there's nothing left to do. Either like depending on how exactly you've set it up in terms of inclusive or whatever, it'll either be you have to guess that amount, so there are no possibilities to recurse on, or you'll have already guessed that amount, so the best value is 0. Cool. So n cubed and that's that. Fantastic. Anything else to mention from this? Definitely so. Done. Okay, problem F. Let's talk about this one. Okay. We'll cancel card. Yes, if you want to go on this.
I read it and I was like, fucking shit.
It should be like some share whiteboard like decreasing.
Yeah, I expect that, but I don't even know how to find that back. So like, bro, I'm not typing it up on the computer.
So do you know like how to find the sum of the
Yeah.
So
With problems. Here.
Yeah, it's just here on one
It's
minus.
gonna be a low push.
and the last number, here's the last number, so it's gonna be
Yeah.
and since it's smaller than 1.
Yeah.
This is F.
So what's the like sum of this?
Yeah,
like
P on the 1 minute.
So in this problem, we are creating a fractal where we start with a triangle and we have a given polyline. Then we just copy this polyline onto each edge of the triangle and then copy the polyline onto each edge of itself and keep recursing it on that. So the first thing that we're going to consider is that we're going to define the area of the polyline. So let's suppose we have the polyline which looks something like this, and we have this is the line of y equals 0. So I'm going to define A2 to be a function. I'll define A2 to be a function of L, where L is this length to here. And A2 is going to be the area of everything that juts out above the y equals 0 line minus the area of everything that goes below the y equals 0 line. So in the example that we're given, we have an equilateral triangle where each of these 4 lines is the same length. And if you calculate it by hand, you find that A2 of L is something like root 3 on 36 L squared. Yep, probably. There might be a constant factor wrong there. But okay, so now I'm going to define a second function, A of L. So A2 of L was just the area for essentially the first recursion of this. A of L is going to be the area once we've done it infinitely many times, recursion. And I mean, in theory, we could calculate this just recursively to some finite precision, but that can be a pain, especially if we have lines of different lengths. So in this case, we have that since all of these lines are the same thing, we're just adding A of L each time on a line that's a quarter of the size. So A of L becomes root 3 on 36 L squared plus A of L on 4. Yeah.
How does that work?
Because there's 4 lines, right?
Yeah.
And on each of those lines, this like thing is gonna be drawn again.
Yeah.
On top of.
Yeah.
So the length is like.
I see. Is that how the recursion is? I thought we were like rotating. So.
Yeah. So, well, we're transforming and then rotating.
Yeah.
So
I know this is a big ask, but would you be able to draw that deep into the recursion?
yeah, please. So if we have the triangle here, if we recurse one more, we get yeah, our original lines were here. Yeah. Here, 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 and here. And so for this case where we have AL is some function involving L and then another case for A, we can recursively calculate this in order number of steps we want to go deep.
But suppose we had the lines were not of even lengths, and we had something like A of L is some function of L plus A of 5L on 12 plus A of 7L on 12. If we try to calculate that recursively, it ends up being exponential in the depth that we want to calculate, which is obviously too slow. So what instead we can observe is that A of L is proportional to L squared. This is a general statement about 2D geometric things, that if you're scaling the length by some uniform thing, you're scaling the area by some uniform thing. And so now if we substitute in AL squared into our previous statement, if we substitute in alpha L squared into our previous statement, yeah, alpha L squared is equal to root 3 on 36 L squared plus 4 alpha L squared thing. And yeah, so from there, we just have a relation that we can solve for alpha, and that eventually gives us an equation for A of L. The hard part becomes then actually calculating A2 of L. So currently I've defined it rather vaguely as the area of the stuff above this line minus the area of the stuff below this line. So imagine if instead all of the points went above this line and their x positions were all in increasing order, so it forms some sort of convex shape above the line. In this case, we could just calculate this by taking each subsequence like that, and treating each subsequence as a trapezium with the points, 2 points above the line and 2 points on the line. And turns out if you just do this, then it works for the general case. So if all the x points are in increasing order, you basically end up just calculating negative trapezium areas, and that cancels out. If you have x's not in increasing order, it gets a bit messy. So you could have some shape like this.
Yeah.
But it still ends up just working out.
Like, this was my issue, like,
I kind of just used proof by AC for this.
Where did that come from?
there can be like cases like this.
As in the line is not like the starting thing is not guaranteed at all to be nice like it was in the sublet, right? So that's the first.
But if you just pretend that it's nice, it works.
Maybe there is some explanation of this in the Toyota.
Yeah.
Maybe. Yeah.
Okay. They're just like claiming it right here. Proved by the editorial says so, I guess. So this is basically the thing we had previously. Calculating each segment, you're getting the width of the segment times the average height of the segment, and it just works. And then for calculating the recurrence relation, in the case where we had 4 identical lines, it was just 4 times A of L on 4. If you have lines of different widths, you just end up summing them together and you just solve for alpha. And
If you keep going, like keep summing through. Yeah, so this is exactly the thing that you have. How would they deal with the particular sum?
Yeah, sure. Different spheres?
Yeah, okay. Okay, sweet. Cool, thank you. Neat.
That was just a math question.
Yeah, it kind of is. Yeah, which is, oh, yeah, okay, cool. Yeah, so, yes, it's a maths question in some sense. I mean, it's doing maths problems with the computer, which is part of better programming. Cool. Problem C. Anyone want to talk about this one?
Was it the one with graph?
Is it
It's
the
the
one,
cable one.
Yeah, where you have the
So,
like put labels on it?
0, 1
Binary,
labels?
Yeah, it's a hypercube one.
Yep. Do you
Hyper-
want to do it?
I didn't solve it.
Oh, okay. Also, cool.
Actually,
Okay, so
The first thing like that came to my mind was like gray code.
Oh,
I can use that
Oh, yeah.
so much.
So this is being recorded.
Yes,
oh,
so
but also you can also read the.
Okay, just.
Yeah.
So in this problem, we are given a graph and then we are given another way of creating a graph in a specific manner. And we have to check if they are isomorphic. And the
So we don't
specific
know what isomorphic means.
isomorphic is basically we can relabel all of the nodes on one graph to turn it into the second graph. And in general, showing that two graphs are isomorphic is NP complete.
Yeah.
However, in this case, the graph we need to show it's isomorphic to has specific properties that we can use to do it more efficiently. So what this graph is we're given some k, and the graph has 2 to the k nodes, and two nodes in this graph are connected if and only if the binary representations of their indices have exactly one bit that is flipped. So let's give an example for small versions.
2024.
So let's suppose we're doing it with k is equal to 2. 2 to the k is 4, so we have 4 nodes. 0, 1, 2, 3. 0 and 1 have exactly 1 bit different. 0 and 2 have exactly 2 bits different. Have exactly 1 bit different. Same with 1 and 3 and 2 and 3.
Notably, this there were multiple questions about the sample input for this one. There was a sample input where it only had 3 of these edges, and so this was not valid BAPC labeling, whatever it is, because you need them to be linked if and only if they have single bit difference.
So some useful properties we can get from this is that each node, you can choose each of the k bits and flip it and get another index in the range. So each node must have exactly k edges leading out of it. Yeah, so
Like, was it supposed to be equal to 2 to the power of k?
yeah, so in this case, I'm saying that k is log base 2 of n. And if k is not an integer, then we just don't have a valid graph. So so each node has exactly k edges coming out of it. The other important thing to note is that the distance from 0 to n is going to be exactly k, because that corresponds to flipping each bit exactly once. You can also see from this that n is going to be the furthest node from k, because you can't flip more than k bits. So let's suppose we ran a BFS from node 0 and we got the distance to each node. 0, 2. So the distance to each node from 0 corresponds to how many bits you have flipped to get from 0 to that node's index. So it's equal to the number of bits that are set to 1 in that node's index. Now let's consider an edge between two nodes other than 0. So in this case, 1 and 3. So let's say we have the edge going from A to B. And let's assume that A is closer to 0 than B. We can basically just pretend that this graph is directed coming out of 0. So it takes exactly 1 bit to flipping to go from A to B, and B has more bits flipped than A. This means that the bits flipped in B are a strict superset of the bits flipped in A. In other words, B is equal to A bitwise ORed with some other value X. So we can, suppose we just take the original graph that we're given and arbitrarily route it somewhere. So if we're given a graph like this, we arbitrarily declare that this node is 0, and 0 must have exactly k edges. For this first case, it's a bit of a special case because for 0, we know the indices of all the things connected to it. It's just all of the powers of 2. And then for this final node, we have 2 edges connecting to it, one connecting it to node 1 and one connecting it to node 2. And we know its distance to 0 is greater than both of those. Therefore, it must be the bitwise OR of that value and something, and the bitwise OR of that value and something. So we can just set it to the bitwise OR of 1 and 2, and we end up with that node being 3. Now, if we go through this graph, we can just check if every index is seen exactly once, and if so, it ends up being a valid network. So let's demonstrate on a larger graph. Suppose we have a graph where k is equal to 3. Each node has exactly 3 edges. So again, I'm going to arbitrarily declare this node at the top to be 0. Since the graph is symmetric, it doesn't matter which node we declare to be 0. And now we can calculate all of the distances. Then we can just number all of the nodes adjacent to 0. And then we number each node below them, the bitwise OR of all of the shallower nodes connected to them. So we end up with 3, then 2 XOR 4 is 6, 1 OR 4 is 5, and this ends up being 7. And if we check through this graph, each of the indices between 0 and n is shown exactly once. And the index of the number of bits in the binary representation of the index of each node is exactly equal to its distance. So it is isomorphic to the original graph. How we would actually implement this is relatively straightforward with just a bunch of cases. So first you need to do a bunch of sanity checks to check if the node has exactly 2 to the k nodes, check that each node has exactly k edges leading out. Then once you've done that, you can pick an arbitrary route and run the BFS, and then just iterate through all nodes in order of their distance and calculate their expected indices. Then just check if the resulting graph is valid.
Any pitfalls that we might anticipate?
If you have two disconnected components, you will probably get bugs, but this is pretty simple to check. Once you run the BFS, if there is a node that is further than k from 0, in the case of disconnected components, that would be infinity, then your graph can't be isomorphic to the original graph.
Any other questions? How are we all feeling? Do we want to continue? There's not many of you are left, and that's fine. We can stop here, or we can do one more. It's up to you. Problem I is the next one up. There is something to learn if you want to, but I honestly just annoying. But I understand it. Yes, it's a data structure. I mean, it's a data structure. It's not the right data structure, really, but yeah. So we can do it or not. That's up to you. Yay, no. Yay. Okay, let's do it. All right, cool.
Like, I was still bad on every other problem, but managed to like finish I in like 25 minutes. So it's like zero bug in it.
Yeah, like if you have the right idea, it's not hard, but
It was like quite big, like almost 200 lines.
yeah, okay. I mean, the structures can be like that. Okay, so problem I, we have this exchange that has a list of buy and sell orders, each with an amount and a price. So yeah, let's look at the sample. So there are two. There are two types of orders: normal and fill or kill, which we will get back to. But if we start with, like to see what happens, we first have a buy order for 7. Is it?
Yeah, 700, but
700
shares.
10 shares at 700. Yeah. So someone is proposing to buy 10 shares at a price of 700. The next person comes along and wants to sell 20 shares at a price of 500. So what happens? Well, whenever a normal order comes in, it's checked whether the newest, the lowest sell price that exists is below or equal to the highest buy price that exists. And if so, those two people get paired up, and whoever runs out first wins. Yeah, so a transaction is made between that sell order with the lowest price and the buy order with the highest price until one or the other or both is completely fulfilled. And older orders are prioritized over newer orders. And we continue this until the lowest sell price is strictly more than the highest buy price. Okay, so the second order is to sell 20 of this stock. There is a higher buy price for 10 of this stock, so we fulfill that order to completion, and now all that's left is an offer to sell 10 of this stock. Cool. Next, the third order is to sell yet more of the stock at an even higher price, so that just gets added to the total. Next, we have a buy order, fill or kill, at price 30, at price 600, sorry. Wanting to buy 30 at price 600. Well, how much is available? Well, there's 10 available at price 500, which is okay, but the other 58 that are available are at a much higher price. And because it's a fill or kill order, either you buy all 30 or you do nothing. You throw it out. Yep. And so in this case, there are not enough sellers to sell you 30 at 600 or less. So you discard the order. However, the next order is at price 900. They're willing to spend a lot on each individual share, and there are 60 shares that are willing to be bought. There's 10 available at the cheap price of 500, and there's 58 available at the more expensive price of 800. We're happy to pay for both of them, so we buy 10 from the second order, and we buy 50 from the third order, and that's the last two lines of output, the two next transactions that happen between order 2 the seller and order 5 the buyer, order 3 the seller and order 5 the buyer for 10 and 50 shares respectively. Finally, there's another sell order added, but it's selling. Oh, yeah, and by this point, all that's left is 8 available for sale, and we add another 42 for sale. There's no one to buy it, so we don't really. Cool. So how do we go about this? N is up to what, 100,000 or something? Yep, 100,000. Okay, so how long does it take to process one of these orders?
Log in.
Sorry?
Like log in time.
Like without any data structures. So if it's a normal order, what can happen?
LON has to be.
Yeah, it can be ON, right? A single normal order. Say you put in a normal order to buy gazillions of the stock at a really high price, then you're going to get matched with the cheapest sell order, then the next cheapest, then the next cheapest, etc., etc. You're going to potentially have lots of transactions take place just off this one order that you placed. Assuming that there were no fill or kill orders, what does this mean about the complexity of the entire algorithm to handle this? If one order can take linear time, if one order might be matched with many previous orders of the other type, then how long can it take in total? That's a trick question. So ON squared is like technically correct, we can do better, right? Sure, any one order could result in matching you against lots of the other type, like a one buy order can match you against lots of cells. But the key observation is that this can't happen every time we put in a buy order. Yeah. If your buy order takes out all the previous sell orders, then your next buy order can't do anything, right?
Yeah.
Can't do the same. Yeah. So here we can think about how many times can orders be cleared from the exchange.
Like for one exchange, one of the order or like buy or sell order should be eliminated.
Exactly. Anytime that a transaction happens, again, ignoring fill or kills, one of the prior orders gets completely eradicated, right? Either the order that you put in gets completely fulfilled, or you clear out one or more of the things that are there already. Yeah. So I can guarantee that over all the normal orders, actually, I still only need linear time. Yeah, because every order gets completed only once. Yep.
Just to clarify.
Yes.
When we have a buy order, are we matching that with the cheapest sell order?
Yes.
Okay.
Well, when you have a buy order, the most expensive buy gets matched with the cheapest sell.
Yeah.
Now,
So the only case where you don't have a sell is if it's like the other way around, like if
yeah. So you won't have any transactions if the cheapest, like if no one is willing to sell and buy at overlapping prices. Yeah. Of course, like the transaction that happens will involve the new order if there is any transaction, because if your new order didn't contribute to the transaction, then that transaction would have happened before your order. Cool. So now we can say that using only the normal orders, we can solve this problem in linear time. Happy? Cool. This is called amortized complexity, right? Any one operation might take n amount of time, but adding them all together still only takes n amount of time. So on average, we can say, as an aggregate, the worst case is n. So on aggregate, they are each individually, constant each. Yeah. This is different from expected or average case running time. There's some probability that it's much slower than this, but with high probabilities. Cool. So now we have to deal with these fill or kill orders, and these ones are not so good. Why?
Because even if there's no possible exchange, you have to put them in the correct places.
Exactly. If a fill or kill 8 orders of the other type until it could do no more, then it would actually not change very much. It would be treated much the same way. But the problem is the fill or kill, right? Say you put in a buy order for a lot of stock at a very high price, then you're going to go through all the sales, and maybe you have to look at the entire N amount of sell orders that came before, and you still did not have enough to buy, sell you enough stock to make your buy order. Then you do not get to delete any of the things that you just walked past, and now you might have another fill or kill buy option, buy offer at the same high price, forcing you to do the same thing over and over again. Yeah. So this is the fundamental problem that buy orders, sorry, the fill or kill orders don't let you actually delete and still force you to walk past. So you want some way of avoiding this, of saying, so what is the fundamental query that we're doing with a fill or kill order?
Asking it whether there was like more than the amount of satisfying orders.
Yeah, so where's the status? Guys. Oh, it's here. Wait. Sorry. Patreon, this is exactly what it was. There's a training at the exact rate or okay, where were we? Fill or kill orders, right? Say there's a fill. Oh. Let's say buy amount A at price E. Yep. Then the query that I want to, in order to know whether this order can be achieved or not, I want to know is, I'm trying to think of notation. Is there greater than or equal to A shares sale at price or greater than. Oh, sorry, not greater, less than. Sorry. Yeah. Yeah, because if someone is selling for a high price, we don't care. If they're selling for a low price, we okay, cool. So this is the fundamental question. Yep. If we can answer this, then I claim that everything is fine. Yep. Yep. Because if the answer to this is yes, what do we do?
For the order.
We just go through and fulfill them exactly like we would for a normal order. And again, rely on that amortization to say that even though I'm going to walk past many orders, I clear them all one by one, so then they won't slow down my future. So if the answer is no, then I cancel it, I do nothing. So if I can answer this quickly, then I'm done. What does quickly mean? How quickly do I need to be able to answer this question?
At least square root 10.
Yeah, basically, n is up to 100,000, and I have potentially n of these questions to answer. So I need to be able to answer such a question in really less than n amount of time. So square root would be fine, log n would be fine, constant would be fine. Yeah. So how do we answer such a question?
Other structures.
We need a data structure. We need some efficient way to organize our sell offers so that I can quickly query over a particular range. So this is like a, like if you index the sell offers by the price point, then this is over a range of indices. So that is from the start of the array up to some index, so some prefix of the array. I want to add up the values in that array. Yep. Cool. So how do I do this?
Symmetry, 23.
Yeah, so
or the decomposition.
I mean, because it's only prefixes, do you need? I guess you still need.
Like, you want to do the same thing for each buy and sell, right?
Yeah. So yeah, okay. I guess segment tree is kind of necessary. I mean, yeah, pennant tree is fine, but segment tree does more things. Yeah, okay, cool. So how to do this? So I'm gonna assume for simplicity that all the prices are small, that is from between 1 and n, yeah, it doesn't really change the problem. Only the relative order of prices matters. So even if the prices are, 100n, you can just scale it down.
Like you can use sparse symmetry or just compress every single word.
Yeah, exactly. Yeah. Coordinate compress and then yeah, cool. So, yeah, now we kind of have to derive segment tree. Otherwise, there's not really much to talk about. Okay, so how to? Okay, say I like. Okay, let's talk about like without the data structure, how we were trying to create this, and we'll see what the problem is, right? Say we actually maintained an array of all the prices. So every index is a price. Yep. Again, assuming that the prices are small, the actual prices don't really, as long as we maintain relative order. And then every time I get a new cell order, I'm going to add the amount of that cell order into that array. So I'm going to have something like this. Yeah. Okay. And then I want to know the answer to this question. Are there at least A many shares for sale at price less than or equal to P? How do I answer this question? Well, in the array, I need to walk the entire array up to price P. Yeah, this will take linear time. So that's because the only bits of the array that I stored were the first one, the first one, the second one, the third one, etc. There are alternatives though. We could do. We could store the prefix sums. We could store the sum of the first one, the sum of the first two, the sum of the first three, the sum of the first four, etc. Yeah. And now I'd be able to query. I'd be able to answer this question really quickly. Yes. Yeah. But it comes at a trade-off. If I want to insert a new order, then I don't just add it in one place. I have to add it to the prefix sum of everything thereafter. So updates are now linear, even though queries are constant. So we need a bit of a trade-off, right? We can't quite have updates in constant time like in this price array, because that will force queries to be really slow, and the other way around is also slow for updates. Sorry. So instead, we need something in between. And the fundamental thing is that we're going to have to store more than just in pieces of information about the array. So we're going to build a segment tree. We're going to store the sum from indices 1 through n of the entire array. We're also going to store the sum of the first half of the array and the second half of the array. We're also going to store the first quarter, second quarter, the third quarter, fourth quarter. We're also going to store the sum of the first 116 and so on. We're going to do this all the way down to individual elements. Let's say that these are individual elements. Now, how would you work out the how would you process a new order? Say there's a new sell order at some price. How would you insert it into this data structure? Remember, all of these cells store the total amount of shares for sale at prices within their appropriate range. So say I have a sell order at price 3 for amount A3 that I need to now add. Well, every range that contains this index needs to have A3 added to it. So I need to add A3 here, and here, and here, and here. How many such ranges will there be? Log n, exactly. Because there are log n many levels, because each level has width half the level above. Yep. However, so this means that updates take log n time, because I need to recurse down until I add it to one slot of each level. The other operation that we have to support is a prefix sum. How long is that going to take?
Okay,
Log n, yeah, why?
because if you want to choose a prefix on the like, on this segment tree, like there's gonna be login layers summing up to that.
Yeah, so if I want to, for example, add up the first 7 things, then I care about this node, and this node. Yeah. For a prefix, I can guarantee that it will only need either 1 or 0 nodes from each of the levels. Do we believe it? Yeah. If you wanted to query an arbitrary range, so not just price less than equal to P, but price between low and high, then it's slightly more complicated. You may need to care about, I think, up to 3 nodes of any one level. But even so, the same kind of argument applies. Yeah.
Could we just write the prefix sum for high and the prefix sum for lower, then subtract them?
Prefix.
Well, like we don't have prefix.
It's the same thing. Yeah. Prefix queries take log n time, and arbitrary queries also take log n time. So like, doesn't matter. Yeah, good question. Yeah, and also, I'll get I'll get back to this, but segment trees do a lot more than just sums. So yeah, so now we have a data structure that lets us query for a price P, for an upper bound of price, then I can query how many sell orders there are, sorry, how many total shares there are at all the prices up to P in only log time, and compare that to the amount A that I was trying to fulfill with my buy, fill, or kill order. I'll have to, of course, make the same kind of data structure for the buy orders so as to treat the sell, fill, or kill orders. And yeah, it works. Every order can be, so every fill or kill order, we can decide whether it's going to be filled or killed in log n time. Every normal order gets added to this data structure, whether this segment tree or the other one, in log n time. And then the only other stuff is the actual fulfillment of transactions, like the actual transactions where one gets matched against another. And I can again claim that this is amortized constant time because across the aggregate of all of them, it's still only. Cool. Yeah, segment tree is really useful. Good stuff. Yes.
Is this available in C++ standard library? Or do you have
It
to
is not.
It's not like built-in library.
It's not in a standard library, so you do have to write this yourself. Basically, you can do the same kind of array construction that I talked about for binary heap, for parity queue. So this is node number 0, this is node number 1, this is node number 2, 3, 4, 5, 6, etc. in an array, and then everyone's children will be, so like node I children will be 2i plus 1 and 2i plus 2. And so you have one big array of size about 3 times your actual n, which contains each of your segment tree elements. And then every segment tree query starts at the root and recurses left and or right, distributing its appropriate amount of stuff. Yeah. So like to do the update query, we would have said update at the root, because the index that I'm trying to update is within the range of the root, make the update here, but also recurse left because it's to the left of my midpoint. Then within the left node, I'll do the same thing. Recurse right because it's in the right half of my, it's on the right of my midpoint, and so on and so forth all the way down. This will take only log n time because it's a point update. You cannot be recursing both ways. You can also do range updates, but they're more complicated.
Lazy.
Huh?
Lazy.
Yes, exactly. Whereas for a query, in a query, you will say, again, start at the top. I'm interested in the range of 1 up to P. That's not like, that doesn't entirely contain this node, which represents the whole range. So I cannot use the value stored in this node, right? That will include some stuff that's outside of my range. So instead, I pass I pass that query down into each half. And I say, you on my left, find the part that you're responsible for, so 1 up to midpoint, and you on the right, find the part that you're responsible, which is midpoint up to P. Yeah. The one on the left is going to say, well, the range that you asked me to find is my entire range, so I just report my own answer. The one on the right is going to say the same thing that the root said, which is part of, I'm not the entire range, but if I split left and split right, each of my children can find out part of the answer for me, and I can pass that up. Yeah. But yes, you can do a lot more than just this. You can do, yes, arbitrary range queries. You can do range updates.
Weighted updates and queries. Sorry, weighted updates and queries.
Weighted in what sense?
For example, like you're gonna add arithmetic sequence.
Oh yeah, there's yep, that's true. You can also do operations other than just sum. So you can do what else?
XOR multiplication.
Yeah, so XOR
Sunset trees, right?
sorry,
I think you can do range reverse sunset.
range reverse, maybe?
That's a bit complicated because like you have to keep track of whether it's reversed or not, right? And
Okay.
but it's up to its children. Yeah, it should be possible.
Basically the same.
Yeah, it should be possible.
Okay, I kind of believe it. I'd have to think about it some more, but yeah, it seems maybe possible. So the operation being proposed here is range reverse. So given a pair left LR, your operation is reverse the range between L and R.
Actually, you might only be able to reverse a binary subrange.
Yeah.
Okay.
Yeah. Because like when
Okay.
there are two ranges intersecting, like there's nothing much you can do about it, right?
Worth thinking about. But you can, so yeah, XOR works, multiplication works, and these are kind of analogous to addition, right? This should be kind of unsurprising that you can do the same thing, but just store the XOR of everything in the range. Maybe more surprising is that you can do stuff like GCD. Yep. Yeah. And that's a bit less like addition because you cannot do the thing that you talked about of prefix high minus prefix low. Yeah. So you genuinely have to do the range decomposition. Yeah, because you cannot do GCD up to high minus like divide by GCD up to low. Yeah. So yeah, you can do all kinds of cool things. Okay. Yeah, that's problem I. Yeah. Are we continuing? Okay. I don't know much of the solutions beyond here, I don't think. So give me a sec, or we will hand off to Jenny. Jay. Okay, Jay's next, so I guess we can talk about this together. I'm not so familiar with the problem, but yeah, if you want to leave, that's totally fine. We have probably reached.
Actually, one thing, is there like a list of form properties that operators you support with a secretary have, like translating this sort of thing?
Almost anything that is associative.
Associative is really the bare minimum.
You can do non-associative.
What?
Right. Like if you do something like maximum non-adjacent subsequence sum,
Oh yeah, true.
because when you're combining the range.
Yeah. But that's like very specific, right?
Yeah, you have to be very careful.
Yeah.
Yeah, anything associative works. If you're doing things that are non-associative, tread very carefully.
Yeah.
Yeah, because like, does it kind of make sense that associative is really all that we care about? Like, we are never going to, yeah, so we're never going to rearrange, like, we're never going to reorder them, so commutativity isn't required. But we are going to rely on the power of 2 bracketing. And so associativity is generally important, but I suppose there are some special circumstances where you don't need it. Yeah. Cool. All right. So what's the problem? We have this platformer game. And oh god.
Yeah, so
Someone want to tell me what the problem is?
I can try.
Yeah, go.
So you're playing the game and every level has like some number like of pixel length, which is like 1234.
So that's the array. That's the
Yeah,
that's
length
this
of the
array.
level.
Yep.
Yeah, so
So n array of length n, those are the lengths of the
Levels.
the levels.
Yeah.
And then this is
FPS, you're like
frame
frames
rate?
per second. Yeah.
Yep. Cool.
So your
And
character
then what
moves
do we try
like
and do?
100 pixels per second,
Sure.
and you want to like finish this game as soon as possible.
Okay.
So every time you finish like a level, your game has to end on a like integer number of like frames. So like on the first level, like there can be like 12.34 like frame, which means it's
Yep.
gonna be have to be 13. But you can change the frame rate to be like anything under the like given amount.
Okay, so you can choose frame rate 1, 2, 3, up to 10.
Yeah. But the like frame can be like fractions. For example, like
Floods. or-
What can be
Yeah.
Okay. All right. Cool. So you can choose any real valued frame rate up to 10.
yeah.
So long as the what the so long as the final state is a full frame. Is that it?
Yeah, so there should be an example like on the sample input tree at the end of the like statement.
Okay.
For example, consider the third sample input.
Yep. Cool. Both levels complete in 15 frames. Is that?
Yeah,
3,000 over 1249.
and that's exactly 15 frames in 6,245.
And
Yeah.
the second one that is not 6245.
Well, that's like 14 frames point like 7 or something, but I think that is the, and when you like take the integer ceiling, it's gonna be 15.
Okay.
So there are like 30 frames, and like when you multiply it by like the duration of a single frame, it's gonna be 12.49 seconds.
Oh, okay. Yep. Wait. So this 12.49 is from exactly
30 frames. Yeah.
okay. Right. So you're choosing the best frame rate so that the ceiling of like you choose a value f dash up to this given f.
Yeah.
And then for every array element, you add AI over your chosen f dash.
Yeah. You want to minimize the sum of every single divisions.
So it's
These all like I had the assumption where you have to like pick one of those with like integer amount of like frames like exactly, but apparently like that was not giving the correct answer for the like last example test case. Maybe like because of the limitations on the things, but if there is like no limitation, it should be like correct.
So is that a correct summary of the problem?
Yeah.
Okay, cool. Right, let's see.
But
it's like this.
F dash is like kind of complicated.
It's not f dash. It's like 1,000 times f dash or something. Is it?
It's like 1,000 divided by f dash times something, maybe.
Wait.
So frame rate.
Oh, right.
Yeah.
Yep. Cool. So it's frame rate.
The question was about dividing this by
This.
Yeah.
And it all needs to multiply by f dash.
Yeah, outside the bracket.
One on f dash.
Outside the bracket, multiply by yeah, on f.
Okay, cool. All right. Okay, so I'm just reading editorial now. So the outside part is decreasing. Yep. So a minimum can only be attained when this thing jumps or when f dash equals f. Yeah. What is that? So yeah, like this is P. Oh yeah, okay. I guess. So the claim is that in any small segment of this function where none of these change through a step, yeah. If I just perturb ever so slightly so that none of these change from one integer to the next, then each of those segments is going to be decreasing. Yep. Yep. So if I want to minimize, then the only possibilities for that to happen are when this decreasing part has gone as far as it can, and then we're about to have it, and then we have a jump, right? Yeah. So at a threshold point where one of these floors is about to jump further, yeah. Because if you go a little bit over an integer, then it jumps up again, right? So you can have a local minimum when one of these things is exactly integer, or at the very end point of the entire function, which is f dash equals f. Okay, so these are the only candidates. Group.
And we don't have to care about that many AI values since the sum is on median. So there can be up to 1414 different values on AI.
Sorry, one sec.
Yeah.
Yeah, so these are the only types of candidates. Okay. Now compute all interesting frame rates, and for each one, find the sum. Claim is that this is too slow. How many of these interesting frame rates are there?
1415.
Explain to me why, sorry.
So the sum of the length of the pixels are up to 1 million. So there can be up to
the sum of the AIs is up to 1 million.
Yeah.
Cool.
So there can be up to a square root 10, different values.
Yep. Okay.
That means it's 1415.
Right.
Okay. So we have to consider f dash to be around 1500 different values. And that should give us the correct answer.
Right. Observation 2, if all jumps are distinct, the total number of frames increases by exactly 1 at each jump.
Yep.
So if we sort the jumps, then recomputing the total time takes constant time.
Wait.
I don't fully get it, but what's going on here? So this is saying if we sort the rate A,
This is if we compute all of the jump times, not
Yes.
just the maximum ones, and we sort those, then each step we go, the sum of the jumps increases by
the sum of the jumps increases by 1, I agree. Okay, sure, that's fine. Compute all the jumps and sort them. Claim is that even if there are multiple jumps that happen at the same time, we just process them individually and that's fine. Compute all the jumps and sort them. For the first jump, compute the total frames. For every subsequent jump, just add 1 frame. And finally, do this additional case where f dash equals f. And the runtime is, oh god, figure of f times sum from I equals 1 to n of ai over 1000 times the log of
Wait, so?
for the sort.
Ah, I see.
Yeah, so claim is that this is dominated by the sorting.
Yeah.
So is that true? Is this the number of jump points? I guess it must be.
Yeah.
Yep. Yeah, I believe it. Okay, and then yeah, and the sum of all the jump distances is bounded by million, so this is only 1,000. F is up to
Up to like
probably
small number. I think it's a small number.
1,000.
Yeah.
Cool. So we have 1,000 times 1,000, a million, 1 million log a million.
20 line.
I missed the constraint on the sum of them less than or equal
Wait,
to
didn't
the
actually-
last 20 minutes.
Yep. Yeah.
Oh,
Yeah, so there's only 1 million there's only 1 million jumps that we might care about. If we sort them, then we can, we only need to spend a non-trivial amount of time on the first one and the very last one. Everything in between is just one more frame.
I might have made a mistake on the order of like multiplication and division. But like there's an error of like 10 to the minus 6, right? But still like,
Yeah,
not sure.
yeah, because there's not actually that many floating point calculations in any one of these. Like not like there's a few of them, but you only like do a multiplication and division of the you had. So you can't exploit that badly. Yeah. Surprised that didn't work then.
Like choosing the F dash is kind of annoying since it can be like a weird number where the number of frame and
What's your team name?
we fell off.
Oh, okay. I didn't pass that. So
No, I didn't.
Oh, you didn't
submit this,
Okay.
yeah, because you didn't pass the last one.
Okay, right. Cool. And then we have K, which is fun. And I don't know what exactly is going on here.
Randomized algorithm.
You can talk about it if you'd like.
Wait, K?
Let's randomize and it works.
Go.
It did not involve much sophistication.
Right. I'll bring up editorial and you can talk, or you can talk through any part that's unclear. But... Okay, so we have. Is that an accurate summary of problem? Multigraph G integer K. What abounds?
K is less than or equal to 6. So.
Sure. K. Yep. Okay. So we want to select some subset of some subset of vertices. So exactly K edges, yeah, have at least one endpoint in the selected subset. Okay, cool. Fine. Yep. Okay. Yeah, certainly if you consider all subsets of the vertex set of the graph, this is hopeless. Yeah. N is up to?
5,000.
Okay, very hopeless. Cool. So we need to do better than this. How can we do better than this?
Right.
Wait, so claim is that our vertex set that we choose should also not be bigger than 6.
Yep.
Is this obvious?
Yep.
Talk me through why?
Like if you pick more than K vertices, like
Yeah, if you pick more than K vertices, then you are necessarily like either some of those vertices are isolated vertices that don't contribute, that don't have any edges from them at all, or each one of them contributes at least one edge, and that's bad. Albert, you could have edges between.
that's gonna increase it.
Oh no, it's still gonna be bad. Yeah.
Yeah.
Yep, sure, that's still bad. Okay, better but still too slow. Because this is n to the 6.
Yeah.
Cool. Okay, how can we get better? Yeah, okay, so you do all kinds of hacks. Okay, remove large degree vertices. If you have a vertex of degree greater than K, then that gives you more than K edges just on its own. So you definitely don't want such a vertex. So get rid of all of the vertices of degree more than K. Singletons and pairs, you have n, like with n equals 5,000, you have n squared time, so you can check every individual vertex and every pair of vertices. That's going to be fine. Remove leaves. This one is very helpful. So if you have a leaf V, then you can try picking that edge, so that vertex, because it only contributes one edge. So now you can reduce the number of number of edges remaining by one, and that gives you every solution containing a leaf. More generally, you can recurse, so you can pick a vertex and then the graph GK is a yes instance if and only if G without this vertex and K minus however many edges come from this vertex is also a yes instance. And I'm guessing this is what you did?
Like, basically.
I feel like the chance of getting the correct thing is quite decent, so.
Okay, that's a lot fancier than my algorithm.
Okay, cool. Read this if you want to understand it. What did you do?
I just like selected random subsets as long as they didn't have too many edges, and eventually it worked.
How do you bias towards picking? How do you like ensure that the random subsets you pick don't have too many edges?
So you look at all of the nodes with a degree less than or equal to the thing you're looking for.
Okay,
If
so
there's one with exactly the thing you're looking for,
you're fine.
found it. Otherwise, you pick a random one of those and you keep looking until eventually you get to a point where there's nothing you can do, and then you just repeat.
Is it accurate to describe this as the recursive solution, but just pick randomly for the V at every stage?
Yeah, basically.
Okay, cool. Thanks. Yeah, so actually pretty doable, but just really scary looking. Okay. I think that's everything then, because yes, certainly that is the hardest problem. That's pretty evil. You already have code golf solutions down to less than 200 lines total.
If they're golfing number of lines, why don't they just put it all on line?
I think that is kind of okay, so we can have a brief look at scoreboard and then that will be all for us. So we can update. Okay, I guess I can do it. Yeah. Oh, but it's. Is it unpresent? It is unpresent, right? Yeah. Cool. So. Thank you, Yoshi.
Oh, by the way, there is like one student from 3.
Yeah, that's Hayden. He's from ANU, but he's on exchange.
I see.
There's one from Canada.
Yeah, that'll be Darcy's people. Darcy had used the server for a local contest in Canada, and so yeah. Cool. So how did we end up? Oh, scrolling past a lot of empty ones.
Oh shit! It reminds me of the IC one.
Oh, yeah.
So we have nearly 100 solves on B and H, not quite as many on them D and E, and then 20 something on A, G, and L, and very few problems. That makes a lot of sense. Yeah. What on Mars? Welcome. Oh, Jay got solved. Who's got Jay? Who's that? Who's OUG? I can probably find this.
Okay, what's your
That's
name?
an initial.
What's your team name?
Very creative username.
Oh, damn.
Yeah, give me a second. I can find out.
I guess Steve is reasonable, but Steve is definitely not.
Just shit.
Less excuses.
Wait, what was the F again?
F was
Ah, I see. Yeah, it's geometry, and we had like 1 hour left. A fun fact, like we didn't make any wrong submission.
What? Oh, nice.
Geo is the art of avoiding floating point errors.
Yeah.
So, okay. I have no idea who these people are. That's strange. Okay. Interesting. I don't think they were here. Were they? Were they physically here? They were not physically here, so. Right, well, they're clearly good. Yeah, so Q is Hayden. Frog for Paint is a team from Canterbury. They have, I think they are retired from South Pacific, I think, because they're like, at least some of them should have graduated. Yeah.
Jellyfish is jellyfish.
Yeah, jellyfish. This is probably Robin, I guess.
Yeah, seems like it.
Yeah, then not there, who knows. Yeah, anything notable? Anyone want to talk about any experience that they had during contest?
Like this was interesting.
Probably you are this one. Nice. Nice. No wrongs in this. Fantastic. Yeah, so just CF. Yeah, I mean,
Wait, serious ambitions
what?
on the yeah.
Nice folks to that. Well, that included like
The range range.
optimizing my range tree to avoid memory exceeding because it was a pointer-based lazy create range tree. of size.
Okay, yeah.
Yeah, like that one is very annoying. Like, yeah, that's why I just compress everything.
That
Yeah,
when you really want to micro-optimize your range tree, you can build it all at compile time.
Yes. Yeah.
I did that once, but then I tried to compile it and like it had been compiling for half an hour and it was
Huh?
using 30 gigabytes of memory and I just gave up.
Wait. Whoa. Okay. That's great. Not so good. Anything else?
I should look up.
Where you guys at? That's fine. Doesn't matter. Anything that you reflected on from doing the contest?
I need to learn state trees.
Okay, that's good. Yeah. Are you doing
Please,
PowerPoint at some point?
I don't know what.
Are you doing from Charles?
I don't have space in my degree.
That's fine. Yeah, it is taught there, and the lectures are public, so you can just run the lecture notes. Yeah, Ethan, any
Wait,
reflection?
who is like Vector Pork?
People who I don't know.
Isn't it even?
Huh?
Isn't it even?
I know they did a snake contest. That was like one of the usernames, I think, but I can't remember who it was.
Like, even in Dorian, we were like making food names last year. So pizza sushi. seems
Yeah,
pretty
I don't
cool.
think it wasn't all of them. They were here, so either I didn't recognize Evan, which is
Like I didn't see you in FL like today.
yeah. If they weren't here, then that team was here.
Oh, I guess. That makes sense.
Yeah, cool. Well done, everyone. Thanks for sticking it out. Thanks for sticking around this long. Yeah, let's go back up and get out of here.
You did a good prophecy. Like I like it.